Hello, everyone. My name is Holly Dinkel. I'm a second-year PhD student in aerospace engineering at the University of Illinois at Urbana-Champaign. And today I'll talk about instance-aware wired network detection and segmentation. This is a picture taken inside the Kibo module on the International Space Station. Wires and cables are everywhere on the ISS. The power and communication system comprises over 8 miles of cables. And my goal is to automate the inspection and maintenance of these wires and cables with robots on the ISS for tasks like knot manipulation, routing inspection, and assembly. So Astrobee could detect and correct anomalies within the ISS power and communication system. And I'm working on developing cable perception and manipulation for Astrobee. A key capability enabling automation of these tasks is individual cable identification and segmentation in a camera image, which I'll refer to as instant segmentation. And in this presentation, I'll provide an overview of my progress in developing instant segmentation for Astrobee. I'll present key results so far, ongoing work, and planned directions. I created a data set of around 1,700 lab scene images annotated with instant segmentation masks. These scenes are similar to the network inspection scene I just showed on the previous slide. And I categorize these scenes into 6 types, where each type is based on the number of objects in each scene. I trained MaskRCNN, which is a state-of-the-art method for object instant segmentation, on this data set and evaluated the quality of the predicted segmentation masks by computing the IOU score for each object in the scene. In all scene types, the IOU for devices is high, around 0.95, where 1.0 indicates perfect segmentation relative to the ground truth label. And the average IOU for cables is around 0.75, which is much lower than the IOU for devices. And a key finding is the quality of the cable segmentation varies by scene type. In the complex scenes with 5 or 6 objects and a lot of occlusion, the average IOU is less than 0.3. I'm currently in the process of figuring out why this is the case and identifying potential solutions. As part of my efforts to get MaskRCNN to perform cable instant segmentation on cluttered scenes with usefully high IOUs, where the goal is around 0.75 average across all cables in the test set and not low IOUs like 0.2 or 0.3 for complicated scenes. As part of this effort, I'm verifying its feasibility through training and testing on a small number of complex scene-only images, as shown in the figures 1 and 2 on this slide. These model overfitting studies suggest that MaskRCNN is capable of performing instant segmentation as desired. 2 questions that my initial results raised are, 1, how suitable is MaskRCNN for performing instant segmentation under occlusion? And 2, how does modifying object instant semantics impact performance? So I modified the annotations for my dataset by segmenting each contour in each object instance mask into its own segmentation mask to create a dataset which is occlusion-free. And I'm in the process of training and evaluating mask predictions on this modified dataset now. This summer, I began exploring generating synthetic datasets from photorealistic rendering using PAVRE. The ultimate goal of this subproject is to cheaply generate automatically labeled high-energy deformable object configurations, complex scenes with many objects, non-iconic perspectives, and physics-based anomalies to use for training and testing deformable object segmentation and manipulation architectures. And finally, a motivating terrestrial application or a cool demo that I'd like to perform is the autonomous assembly of network infrastructure given a network design. So for example, tell a robot to pick an Ethernet cable from a bin and insert the tip into a desired port on a router, which would require the integration of perception with planning. I'd like to acknowledge my current collaborators who have been instrumental in the ideation and realization of this project. All of my collaborators have been involved with all technical aspects of this project, from dataset scene design, dataset collection, dataset annotation, model training, model evaluation, and explainability of results. They have also helped guide project motivation and placing it in context, so I'm grateful for their support. And here's a video of one of the models that I trained on wires on a table in the lab, just to kind of show sort of how this works now. So thank you for your time and attention today, and I'd be interested to hear your thoughts and questions.